Okay, so this is going to be this problem, which is 2019. It's the second problem set, and it is problem number 1. So I'll go ahead and turn the light on. I don't know if that helps make it a little bit easier to see. All right, so as you can see, we've got a mass hanging down here that goes over a pulley that is, it tells us that the pulley is negligible mass and negligible friction. So that means the pulley has no effect on what's going on. It's just changing the direction of the force. It's attached to a block of mass M, which is then attached to a block of mass 2M on an inclined F theta. And so the first thing that they ask me to do is they say draw free body diagrams for this block and this. So that's the first thing that I'm going to do. So we're going to start with A. And so we have this incline of the hill here, and this is the little mass, the block M. So the first force that I always think of that acts on a body is gravity. So I'm going to draw that one, and gravity is always straight down. So I can call it F sub G, or if I want to, I can call it little m times G, either one. All right, then of course it's sitting on a surface, so I must have a normal force, and that normal force has to be perpendicular to the surface, so it's got to be a right angle to the surface. So it looks like this, and we label it normal. And if I look at this block, it has two ropes tied to it, one going this way, which they label as T2, and one going this way, which they label as T1. So I'm going to call this T2, and I'm going to call this T1. Now, of course, my little m's in there, but that was on the original diagram, so it would be there as well. Now we're going to look at this big one here. Now, as this one is going down, we're going to draw him. First force I automatically think of is gravity. So I have force of gravity, which is F sub G. It's also big M times G, so you can put either one of those. And then this is not on a surface, so I don't have normal, but it's supported by a rope. And I would normally just call that tension, but again, this pulley has no effect, and it goes over, and I see that that is the same as T2. So I go ahead and I put T2 there. So this is the free body diagram that would be for part A. In part B, it says derive an expression for the magnitude of the following. If you need to draw anything other than what you have shown in part A to assist your solution, use the space below. Do not add anything to the figures in part A. So what they're telling me is don't draw on these because you might lose points because you put extra vectors. So I'm going to redraw them. So I'm going to go ahead and put these on here. And you notice I left a little space over here. I'm going to come back and put that third block in there. So this is little m G. This is normal. T2 and T1. So this is little m. Then I've got big M, and he has gravity and T2. But I got this other block, 2M, and 2M is down here on the bottom. And he only has three forces, gravity, normal, and then this T1. And so we'll put him, his gravity is down, it's 2mg. His normal is, again, perpendicular to the surface. If you need to, draw yourself a surface in there so you can see that. And then he has, T1 pulls down on the middle block, but it pulls up on this, so that's T1. Okay, so now I've got the free body diagrams for all three. So now I'm going to look at what they're asking me to find here. So they're asking me for T2 exerted on the mass by the string. So I say, okay, well, here's the easiest thing to do with T2. So I'm just going to write that. So if this thing, I go back to the beginning, and it tells me that these are held in equilibrium. And equilibrium means everything is balanced. So equilibrium means the ups equal the downs, the rights equal the lefts, everybody's happy. So that means T2 is up. It must equal mg, which is down. For this one, he has components here of gravity, and this is what they didn't want you to draw on these diagrams. Remember that whatever the angle of incline is, that's the same angle that appears between your y-axis and gravity, so this is theta. And so then this side will be mg sine theta. This would be mg cosine theta. This one is the exact same, except it's 2 mg. So it's 2 mg sine theta and 2 mg cosine theta. All right, so now, once I have that, then I'm going to write equations for these two. So let me do a little shimmy here. Okay, we got that guy done. We'll put a divider in here so we can keep them separate. So this one, the things that are this way have to equal the things that are this way because it's in equilibrium. So who's up the hill? Only T2. Who's down the hill? Well, T1 and this guy, mg sine theta. Now we look at this one. Same thing. Things that are this way have to equal things that are this way. Now, I know that normal and this force here cancel each other out, so I'm not going to write those because I don't need those in this part of the equation. And so now the up the hills on this one is T1, and the down the hill is 2 mg sine theta. Now that I have those, I'm looking for T2, but I have it here, but I don't know what m is, and I'm not allowed to leave my answer because remember my answers has to be in terms of m, theta, and g. So I can't do big M. I've got to do little m. So I can't use that one. So I'm going to go to this one. And I say, well, I could find T2 if only I knew T1. But I go over here to what I just did and say, hey, I do know T1. So I plug that in, 2 mg sine theta plus mg sine theta. And so T2 is going to be 3 mg sine theta. And that's my answer for what is T2. So that's I. But we're going to keep going with this because now I says what is m such that it can remain in equilibrium. So I'm going to put, instead of T2, I'm going to put this. So 3 mg sine theta is equal to big mg. So I cancel out my g's, and m is equal to 3m sine theta. And so there's what m is that will remain keeping it in equilibrium. Okay, now we're going to go to C. Ci says, okay, now this is going down, these are going up. This hits the floor before these hit the pulley. So when this hits the floor, what happens to, on I, what happens to T1? Does it increase, decrease, stay the same, or go to 0? Well, it's going to go to 0 because when you lose the pull from this side, you lose that tension. When you lose that tension, this one was already going up, and so this one was already going up as well. And so this tension in between, you can imagine that rope just goes slack. And so on I, it's going to be decrease to 0. On 2, it says, is the velocity of the block of mass m up the ramp, down the ramp, or 0? Well, the velocity, they're already going up the ramp. So when we cut the string, they're going to continue going up the ramp for a little while because they've already got forward momentum that way, and they have to be slowed down. So they're going to go up. So that's going to be up the ramp. And on 3, it says, is the acceleration up the ramp, down the ramp, or 0? Again, we're talking about this middle block. It's going up the ramp, so its velocity is up, but it's slowing down, so its acceleration is the other direction. And we can look at our free body diagram and see that if I cut these tensions out, the only thing that's acting is this gravitational component here, which is down the ramp. So that's going to be down the ramp. Okay. Now we move on to a little bit more complicated situation. So this is a little bit more difficult than these, but not too bad. It says, consider the initial setup, and now suppose that you have friction. And so now we're going to find an M that will keep the blocks from moving down the incline. So what's going to make it stay in equilibrium? So I still want it balanced. So I'm going to go back to these diagrams that I had a minute ago. And we'll go ahead and draw them again. so that you can see. This is the 2m block, and remember that we had 2mg, T1, and normal. Now remember, if this block is wanting to slide down the hill, friction is going to be acting in this way too. So then we got these two components, so 2mg sine theta and 2mg cosine theta. All right, the M block in the middle, well, he's got the same type of setup going on. He's got his normal, he's got his T2, he's got T1. He wants to slide down the hill too, so friction's going to act like this. It could really be drawn on here. You could say T2 plus friction. I draw them separate, so you do see there are separate arrows. And of course, he's got gravity of mg. And so his gravity component, he has mg sine theta and mg cosine theta. And then we draw the big one, and he doesn't change. He has mg and T2. Okay, so we're going to rewrite these three equations again. And I want it to be in equilibrium, because it says, what does this thing have to be so that this does not slide? So that means that everybody's got to be balanced. So for these two, it's got to be the ups have to equal the downs, the ups have to equal the downs, and this one it's up equal down. Now I know these do not equal directly up, but this is the plane that this block is moving in. So we look at this and we say, okay, so T1 and friction are that way, and then this 2mg sine theta is down. For this one, T2 and friction are to the right, T1 and mg sine theta are to the left. For this one, it's still T2 equals mg. So I'm looking for what is that m, but I gotta find T2 first, so I gotta work my way back through it. So the first thing I'm gonna do is I'm gonna deal with this friction thing. Friction is fun, remember, friction is mu n. So I'm gonna put in mu and then times n. Normal is gonna be equal to this gravitational component. So normal is gonna be 2mg cosine theta for this one, and for this one it's gonna be mg cosine theta. So I'm going to put that down here. So 2mg cosine theta is equal to 2mg sine theta. Okay. All right, so this is going to give me something to do with T1. So what I'm going to do is I'm going to rewrite this one. So I've got T2 plus mu static times mg sine theta is equal to T1 plus mg sine theta. Now I'm going to write this equation because I love elimination. I'm going to put this underneath this. So I've got T1 plus mu times 2mg cosine theta is equal to T1 plus mg sine theta plus 2mg sine theta. Got a little bit bigger than I had room for there. Okay, now I've got, no, hold on. Let me erase that. Nah, that's not right. I was meaning to write this. T1 plus mu static times 2mg cosine theta is equal to 2mg sine theta. Sometimes we make mistakes, and that's okay. All right, so I put plus. Okay, so I'm going to add this equation and this equation. When I see things, I have a T1 on the left side of the equal sign and a T1 on the right side of the equal sign. So I could subtract T1 from both sides and eliminate those. So then I start adding things together. So I've got T2 plus, I've got mg cosine theta times mu and 2mg times mu. So how about 3 mu mg cosine theta? And then over here I've got mg sine theta and 2mg, so that means I've got 3 mg sine theta. So now I can just move this to the other side. So T2 is going to be 3 mg sine theta minus 3 mu mg cosine theta. And then I'm going to take that, and I'm going to put it in this. So I'm going to set that equal to big M times G. Now, I'm going to divide through by G. So divide G, divide G, divide G. So this goes away, this goes away, this goes away. I know there's a T2 over here, but T2 and mg are the same thing. So I can just kind of forget that exists. So then I've got 3 m sine theta minus 3 mu cosine, mu m cosine theta is equal to m. And so that is the m that prevents us from sliding down the incline. Okay. Now on E, we're going to use kind of what we have here to do E. It says on E, it says now we're going to cut the string. And so now we're going to have sliding friction. Coefficient of kinetic friction is K. And it says how fast is it going to be going when it reaches the bottom of the incline. So I'm looking for V final. And I know that originally they start at rest. And I know they're going to travel a distance d. So this is really starting to look like a third kinematic. I just need acceleration. And if I could find acceleration, then I can build the third kinematic from here to find out how fast I'm going. So I say, well, what is my acceleration? Okay, well, I'm going to write a net force equation for each one if I cut T2. Okay, so T2 is now gone. We're going to cut that out. And so we're going to write a net force equation. So I think that they're going to accelerate down the hill. Okay, so I'm going to write a down the hill is equal to down the hill, whoops, minus up the hill. I don't know what happened to my arrow there. Okay, so the 2m block, let me fold this back so you can kind of see my free bodies here. There we go. Okay, my 2m block that I have right here at the beginning. All right, he's going to have, it's going to be his, this is his net force. So F net, which is MA. So 2MA is going to equal the things that are pulling him down the hill, which is going to be 2mg sine theta minus the things that are pulling him up the hill, which will be T1 and friction, which is going to be mu times 2mg cosine theta. And this is mu k. There we go. All right. The m, this one here in the middle, he's also going to accelerate this way. So he's going to be the down the hills minus the, whoops, up the hills. There we go. Okay, so his is going to be MA, because that's his net force. The things that are pulling him down the hill are T1 and mg sine theta. And the thing that's pulling him up the hill is only friction, because remember I cut T2. So T2 is now out of the ballgame. So I just get to use that. So that's going to be mu k times mg cosine theta. Okay, so now I've got these two equations. So again, I love to eliminate and solve for things. So we're going to go ahead and do 2ma is equal to 2mg sine theta. And I'm going to distribute this minus. So minus T1 minus mu k times 2mg sine theta. And I'm going to write this equation underneath it. So MA is equal to T1 plus mg sine theta minus mu k mg cosine theta. And so then I'm going to take those. 2 plus 1 is 3. 3ma is equal to, I got a T1, a minus a T1, so that gets rid of those. 2 mg sine theta and 1 mg sine theta is 3 mg sine theta. Minus 2 minus 1, so that's minus 3 mu mg cosine theta. So now we can do some elimination. I see a 3 everywhere. I see an m everywhere. So there's my acceleration. Not so clean, but we'll write it out. G sine theta minus mu k g cosine theta. And then I'm going to take this and I'm going to plug this back into the third kinematic, because now I have my acceleration. So V final squared is equal to V naught squared plus 2a delta x. So V final is going to be the square root of all of that. Well, this is 0, so that goes away. And then my acceleration is g sine theta minus mu k times g cosine theta times my distance of d. And I'm going to leave my answer just like that.